up to T of Vj Wm. Okay? And if you put all these coordinates and make a matrix out of it, you're going to get this matrix, and this is precisely what it is actually. Okay? So if you put, say, if you make a matrix, okay, in which the first coordinate is the coordinates of T1 with gamma, so this would be the first row of it, so similarly the second row, and this would be the jth row of it. So you take each one of T of V1 and express it in the terms of the gamma, you're going to get such a coordinate vector, okay, and put all these coordinate vectors and make a matrix, so you get a matrix actually. So this would be the beta gamma representation for the linear transformation T, for the linear transformation T, okay. And as I said, that in this situation, in this given setting, finding such a matrix is not a big deal. Why? Because what you just have to do, compute these vectors T of V1, T of V2, T of Vn, and compute these inner products as per the definition of W, okay, whatever the definition of W is. So you're going to get what you call the matrix representation of the matrix actually. So as I said, the second part is your exercise actually. Alright. So where we are heading next? The next topic is an interesting topic. It is interesting in finite dimensional cases, in case of the finite dimensional vector spaces, but it is more interesting when the things are in infinite dimension actually, and probably in our discussion here we will restrict ourselves only to the finite dimension actually. Okay? The infinite dimensional case you're going to study in function analysis. Basically the function analysis, the subject that you're going to maybe study in the next semester, is actually infinite dimensional linear algebra. So you're going to do another course on linear algebra, that is function analysis, and it is basically infinite dimensional linear algebra. Okay, so the linear algebra is going to be always there with you. So if you have to do mathematics, if you have to do anything that depends on mathematics, like physics or any quantitative sciences subject, you have to master the linear algebra in its entirety. Okay, this is what that leads to. Okay, the next section is on finding the adjoint of linear transformations, and matrices. Okay, so how to find a linear transformation of linear transformation and the matrices actually. Okay. Roughly in finite dimensional case, every matrix can be thought of as a linear transformation, and every linear transformation can be thought of as a matrix actually. So if you define, for example, the notion of adjoint, say for example from linear transformation, it should not be difficult to take that definition to the level of defining the adjoint of the matrices. So in finite dimensional cases, really linear transformation and matrices characterize each other. Okay, so this is the key thing that we always have to appreciate actually. So for this discussion, so what I'm going to do, throughout this section, throughout this discussion, I'm going to assume that V and W are inner product spaces, both inner product spaces with inner products say this is going to be the inner product on V, and this is going to be my notion for inner product in W respectively. Okay? This is what that is. Okay? At the moment, we don't have any restriction on the dimension of the inner product space. They could be infinite dimensional, they could be finite dimensional, but if I have to prove some specific results, maybe some results require us to restrict our inner product spaces to, say, for example, finite dimensional. But the definition and the basic results that I'm going to prove now, or the examples that I'm going to give, are going to be are true in are valid in any infinite dimensional case, actually. Okay? Any infinite dimensional case. Alright. So here's a definition. So suppose T is a linear transformation from V to W. Be a linear transformation. Then a map. Okay. Since adjoint is an adjoint of the T. Okay. Since adjoint of a linear transformation T is an adjoint of T, so it is something that depends on T. So I want to introduce a notation for it. So is a map T but star. Okay. So for the adjoint of the map, I'm going to use this. So T star is a map from W to V. So if T is a map from V to W, then T star, the adjoint of it, is going to be a map from W to V, such that following is true. Okay. So T of V, W, the inner product of T of V with W is equal to the inner product of V with T star W for all V from V and W from W. Okay? So one thing is sure, W is an element in W and T of V is also an element in W, so this is the inner product in W, while this is the inner product in V actually. Okay? So, for a given linear transformation, a map T star from V to W, a map T star from W to V. You have to take care of it that, okay, if the T is from V to W, the T star is going to be from W to V, is a map that satisfies this identity for all V in V and W in W. Okay? For all V in V and W in W. Okay? So there are many benefits of studying adjoints. You will see actually that the adjoint operator or the self-adjoint operator plays. I'm going to define in a moment that self-adjoint operator is what. They play a pivotal role in theory of differential equation. They play a pivotal role in physics, in many places actually. Okay, so these are some of the basic notions. So if you have a transformation from V to W, then a transformation from W to V is going to be adjoint of the T. Okay. So I must complete that. Is called the adjoint of T. T star is adjoint of T if the T and T star satisfies this actually. So T of V inner product with W and W inner product is equal to V T star of W for all V in V and W. Okay, so this is what you have to do. I'll do plenty of examples. I'll at least give 3-4 examples in which for a given linear transformation we will try to find the adjoint. But is it necessary that every linear transformation has an adjoint? The answer is it is not necessary. So we're going to do one example where you have a linear transformation that do not have any adjoint actually. Okay? So this is what is the case. So here are some of the basic properties of the adjoint. So here's the theorem. So it says that T star that you have defined in this manner, so T star that we have defined in this manner is a linear transformation itself. It's a linear transformation itself, and if T star exists for a linear transformation, it is unique actually. It is unique. Okay? So for a given linear transformation, the adjoint is a linear transformation. So first of all, for a given linear transformation, can you always find an adjoint? The answer is no. I'm going to do an example in which we can't find adjoint. So for a given linear transformation, if there is an adjoint, then that adjoint must be linear and it must be unique actually. Okay? So we're going to try to prove the both of these things. Okay? So how to do it? So in order to do it, let's take U and V from W. U and W from vector space W, and let's take A and B from what do you call F. And what I would like to show that T star of AU plus BW should be equal to A times T star of U plus B times of T star of W. Okay? A times of T star of U plus B star of W. We'll see that, this strange looking notion of adjoint turns out to be very interesting quantity in different contexts when we're going to do a lot of examples for it. So this is what that we would like to verify. And in order to verify this, what I would like to do, I'm going to take a vector from V, okay, from V, and take its inner product with, say, T star of AU plus BW. Okay, so I took T star of AU plus BW. Now by this definition, if V T star W is equal to T of V W, so it's roughly you can say it like that. If T goes on to the other side, it becomes T actually. So in other words, using this identity V T star W equal to T of V W, by definition, this is same as TV AU plus BW. Okay? But this must be in V norm and this must be in the W norm actually. Okay? And then what you can do, obviously, I can use the linearity in the second component, so I can say that this is going to be same as TV U. I can pull this A out, so it's going to become A bar, okay, plus B bar and TV and what do you say? TV and W, okay, in W. In not W but in the product V. This is what that you're going to get. And now on these two inner product, I want to again apply this property. Okay, so I want to throw this t onto the other side of other component of the inner product. So it's going to be a bar v t star u plus b bar v t star w. Okay, and then let's apply, for example, this a bar, multiply this a bar with the second component and b bar with the second component here. So you're going to get v and put them together. So you're going to get v a t star of u plus b t star of w. Okay, and this is true for all v in v. Okay. So on one side I have this, and on the other side I have this. So if I take this onto the other side and put the inner products together, so I'm going to say that this is going to be equal to, this implies that this is going to be equal to inner product of v of the t star au plus bw minus a t star of u plus b t star of w is equal to 0 for all v in the vector in the product space. Okay, and then we proved the result actually. So this is a kind of a vector. This, all of this stuff is kind of a vector which is orthogonal to every single vector in the inner product space V. And then in fourth chapter we proved this result, and I used it previously as well. Okay, that if I have a vector u that is orthogonal to 0 for all v in V, then this u must be 0. Why? Because there is only one vector for a given inner product space which is orthogonal to every single vector actually. Okay? So if this is true for all v in V, so you can say that this must be, in other words, this quantity must be equal to 0. And once this quantity is equal to 0, you got what you want actually. Okay? And this shows that T star is a linear transformation. Okay? It's a linear transformation. Why adjoint, if exist, is unique? Okay, so let's talk about the case that why T star, if exist, is unique. So what is the proof of uniqueness? Okay, so here's a proof of uniqueness, that let S be another adjoint of T. Okay, so let's call S be the another adjoint of T. So if it is an adjoint of T, so it must satisfy, what do you call this, TUV equal to USV. Okay? TUV equal to USB. Okay? But TUW equal to USW. This is what that you're going to get. Okay? But since S is the adjoint of it, but this is also equal to what do you call V T star of what do you call W. This is also equal to this, and hence you have V T star of W, and I have V, but should be U. Okay, so U T star of W, and I have USW. Okay, they both are equal for all U in what do you call in V. Okay, in V. Yes, so they all are equal in V. So by the same argument, you can say, so I can take this on the other side, and then I'm going to have U inner product with T star of W minus SW, and since this T star of W minus SW is orthogonal to every single vector in the vector space V, so their difference must be equal to 0, and hence these two should be equal to 0. So if such an identity holds for all U in the inner product space V, then these two should be equal. Actually, there is no other choice. Okay, so this shows that T star of W is equal to SW for all W in W, okay, and hence the T star is equal to S actually. So this shows that the adjoint must be unique, a linear transformation. Okay, if there is an adjoint, that adjoint must be unique. So I hope you got some glimpse of the proofs of it. Okay, so let's do some examples of it, and let's think about the adjoints of matrices and linear transformation. So the examples will reveal actually that these mysterious looking adjoints are very interesting quantities. Okay, and they play a very important role in several of the applications actually. Okay, so at the moment we're just doing theory, but we can see several applications later actually of it. Okay, so here's an example. Let's take V to be, what do you call, Fn, where F is field. In other words, it is Rn or Cn, okay, and W to be Fm, okay, W to be Fm, and both of them are there with the standard inner product actually. So we know that what is the inner product on Fn and Fm actually. So inner product on this is the scalar product, okay, or the dot product, and on this you also have a dot product actually. So both have the dot product with U. So let's take a matrix A that is an n cross m matrix with entries from F. So A is a matrix with entries from F. And corresponding to this A, let me define a linear transformation TA that swallows a vector from, say, W and spits out a vector in V. Okay, swallows a vector from W and it swallows, say, a vector from V and it spits out a vector in W. And you define the TA operated onto a vector V to be a vector. I need to write, say, VA as an outcome actually, yes. So since A is n by 1, so 1 by, yes, this is 1 by n order and this is n by m, so their product is going to be 1 by m. So it's a vector it's an element in W. It's an element in W because its order is 1 by m. Okay. So what I would like to do for this transformation TA, we can prove that this TA is a linear transformation. TA is a linear transformation, and it's easy to do because the matrix multiplication is distributive actually. Okay. So it preserves the scalar multiplication and matrix multiplication, the scalar multiplication and matrix addition. Okay, so T is linear transformation. You can verify it for yourself. But what I would like to do, I would like to compute the adjoint of this matrix actually. Okay, the adjoint of this matrix. So for that, what I need to do, I need to calculate TA of V, which is an element in W, and take its inner product with W. Okay, and this is an inner product in W. Now, what is the inner product on W? So I can also write that this is VA W. And what is the standard inner product on W? So this standard inner product on W is basically what do you call W star times VA. Okay, W star times VA, because I have this definition. And now I can rewrite this guy. So the Y star AX is A star Y. So there is associative law that is true. I think W star must be, and by W star I mean conjugate actually. Okay, so you have to keep in view that here W star means conjugate. Okay, so I can write this as, so this matrix multiplication is associative. Okay, so this matrix multiplication is associative, so I can write this as A W star. And I know that conjugate is like reversible actually. So this is same as W A star and it's a star actually. Okay, so if you take W A star star, so you're gonna get this. Now if you write this more explicitly, okay, if you write this more explicitly with this definition, so what you're gonna get? You're going to get the inner product of the V with W A star. Okay? With W A star. So hence the T star corresponding to A now is a map that operates on W. Okay, and gives you W A star. So this is really the adjoint of the linear transformation A. The linear transformation A. I mean, if you're going to look in the book, the calculation has been done in a bit different way, but the essence is same actually. Okay, the essence is same. So for this linear transformation, the adjoint is E star A. Okay. So instead of taking, for example, instead of taking say this linear transformation, if I for example take only the matrix V actually. By the way,